storms and the people that studied them. So it would like kind of natural to give the name of the people who studied that storm, right? So that's one idea. But I've been talking to a few people that have different ideas. So we need to meet and then come up with some, there's so many storms that we can find, different rules for different. Actually, with this week, we had two high school students doing some internships at Ifremer, and so we're a bit of an activity for them looking at storm properties. So probably we find two storms and give them their names to the storms. That would be fun. Outreach with that. But yeah, we'll see.
Likewise, people discovering stars.
Exactly, right? The galaxies, some numbers in some catalog. Exactly. The comet is a discoverer as a name.
So, but Luigi has stopped.
Yeah, we found a storm, and he wrote a paper about the swell from that storm, so I think it was perfect. And he was happy with it because some people, may not like that they have a name of the storm. So of course, if you don't know Luigi, there's many people called Luigi. It could be Mario and Luigi, whatever. But for us, we know, and so some colleagues maybe would not like that they have a name of a storm that has a lot of damage and not negative impact, right? So. But very often these big storms are in the middle of the ocean. So the swell can do some damage, but maybe not the storms. So I need to organize a meeting with a bunch of different people that were interested in this topic. Nobu Mori is one of them, and a couple of colleagues. So if somebody's interested in naming storms, you can join the discussion.
Let's start. Possiamo cominciare?
Sì, certo.
Scusa, una domanda. Se parla nella posizione in cui era prima, si sente bene o deve avvicinarsi di più al microfono?
Io sento bene.
Ok. If you can stand when...
Solo che la camera è frizzata.
Scusa?
La camera non si muove, frizzata, e anche non vediamo nessuno schermo condiviso.
No, è che c'è l'opzione, penso, dell'offuscamento dello sfondo, per cui quando si allontana si offusca. Se togli quell'opzione,
Ok, che
dà un po' fastidio.
Yes, because or what I could do is
if you put the option for the background.
Exactly.
Sì, abbiamo capito, adesso
Okay.
Un momento qui.
Ok, no. Ok.
Normalmente ci sarà bene. Ok.
Va bene adesso, giusto?
Sì, solo non vediamo lo schermo condiviso ancora.
Adesso sì.
No, il background is okay. No.
Background is okay?
Background is okay, and can you see the presentation?
No.
Okay.
Of course. Partager. Autoriser. And now if I click here, like I did before. Yes, here. And now,
Yes, we can see now.
Grazie.
Okay, in the presentation mode, correct?
Now it's not in the presentation mode.
Wait a second. Let's continue de partager. That should be okay.
Now, yes.
Okay.
Thank you.
Okay. It took some time, but at the end we are ready to start. So I will make a short presentation of today's speakers. Fabrice Ardhuin is from CNRS, but part of a LOPS laboratory in Brest. He's a global expert in waves and interaction with Earth, atmospheres, highs, and many other things. When I asked how to present him, he said, say just waves, okay, just waves, and the role of waves as in the Earth system. And today's presentation will be about satellite mission SWOT mostly, and how to use this satellite-derived data to measure waves and other stuff. Please, Fabrice, thank you.
Thank you, Elise. So it's a pleasure to be here. Thank you for the invitation. I think it's probably the second time I'm giving a seminar at ISMAR. Actually, the first one was in 2002 when Luigi invited me to the Palazzo. very different setting. I will never forget that. Oh, no. Here it's very nice. Also, it's just different, and I really like it. So thank you very much. And so I'm actually on my way to Vienna for the Living Planet Symposium organized by ESA next week in Vienna. So it's a big remote sensing, all the European Space Agency project will be presented there. And especially there will be a special session dedicated to what now people call it SWOT altimeter. So altimeter that measures the sea level, but not just below satellite, but making images of it. This small piece here is a small piece of the sea level. And we actually have thousands of kilometers along the track with this kind of stuff. So what you can see on this image is the sea level going from 0 to something like 15, 20 centimeters. The scale is about 40 kilometer by 40 kilometer. And the fingerprints you see here, so I colored them in blue, so it looks like the ocean, but this is actually a swell, so very long waves, so about 1 kilometer wavelengths in the middle of the Pacific. I will talk more about that. And so what I will introduce briefly is the ideas about measuring waves and the size of the waves, so not just the wave height, but also the wavelengths. And I will introduce also a little bit more the SWOT mission, which was launched a few years ago and what it measures, what it does. So my title is sizing the largest ocean wave. So largest in this talk will be specific to a storm that happened in 2023. So it was the largest storm in terms of wave height on the globe. And when I was working on that, I got a phone call from a journalist just before Christmas, but very big waves of Peru. And there was actually a much bigger storm we also started studying in December 2024, which we called Eddy. And now we have this game of giving names to storms, because we realize that hurricanes and typhoons have names, but actually these are not the largest waves in the ocean. The largest waves usually come in extratropical storms, and they occur offshore, and not many people care about them, except that they will make some swell, and I'll show you some of that. So I will discuss what kind of measurement we have for these big waves, and what we can learn in terms of the physics of the wave evolution, in particular what people that study waves call the four-wave interactions. And then I'll finish up with trying to improve the numerical models for waves based on these new measurements. Okay, so scales of waves. So this is a very old plot coming from Walter Mang from 1950 to give you an idea of the kind of time scales of the oscillation of the sea level we're looking at. So typically my wave world is on the left, mostly between 1 second and 30-second periods is what we would call ordinary gravity waves, or wind waves. These are generated by the wind, and they propagate, and so they have a dispersion relation. So typically a given period will give you a given wavelength. So 1 second is 1.5 meters, and it goes with the square of the period. So if you multiply by 10 the period from 1 second to 10 seconds, you have to multiply by 100 the wavelength, so it's going to be 150 meter wavelengths. And so the kind of thing I was showing you just before was 1 kilometer wavelengths are actually waves longer than 23 seconds. They don't happen very often, but often enough that we actually have a lot of data of that. I will show you some of that. And of course, the surface gravity waves for a much longer period will be influenced by the Earth rotation, and we'll get to tides and everything. Okay, so this was a sketch. This is actually measurements of so it's a bit of a funny thing. So it's the acoustic level measured at the bottom of the ocean in a place north of Hawaii. This is from a paper from 2012 from Dunabi et al. And they had a hydrophone measuring the pressure, and they recorded for 1.5 years, and they classified the measurements as a function of wind speed. So they have the colors here are the wind speed going from blue in 2 meters per second to 14 meters per second in red. The x-axis is the acoustic frequency, so 1 hertz is right there, and then you have different things. So you can see that there's a clear change with the wind speed. So wind is explaining a lot of what's happening on the ocean at high frequencies, and some of that above 100 hertz is just bubbles. We think we now have a good theory for what's happening all the way to up to 3-4 hertz, and models are starting to be able to produce also the acoustic pressure. And this is actually due to wave interaction at the surface, which generates some noise you can record at the bottom of the ocean. The shape of this spectrum follows the shape of the surface elevation spectrum. At the longer periods, typically more than, so that would be 5-second acoustic, but in general, it corresponds to twice the period, twice the period for the ocean waves, so more than 10 seconds. The dependency on wind is not so strong because the waves at that time, at that place, are not generated by the local wind, but they can come from a different storm. It's what we call swell that propagates out of the storm and goes to other regions. So some of the challenges of studying ocean waves, as I was pointing, so there's issues for the shape of the wave spectrum, not so much the energy level, but the directional distribution. And the plot I was showing just before is actually very strongly dependent on the presence of waves in opposite direction. And that's very sensitive to the directional widths and the details of the directional distribution. So until a few years ago, all the models were very bad for predicting that directional distribution above 0.5 hertz. So that these are waves shorter than 3 meters, so they are relatively short waves. We're now starting to have something that kind of works, but there's still many other things that we still don't have a very good answer for because they are nonlinear effects. And so, for example, the statistics of the sea level and how the sea level is correlated with slopes. It sounds like a very specific, stupid topic, but actually this is the reason why when we measure the sea level, we have an error in the sea level, which is about 3% of the wave height. This is because of the correlation of the slopes and the elevation. And so 3% of 2-meter average wave height is 6 centimeters. So people have known that since they measure sea level with altimeters, and they called it a sea state bias. And so they have some empirical correction for it, but still no theoretical base proper parameterization. And so for SWOT, which is starting to measure smaller and smaller change in sea level, it's probably starting to be an even bigger problem. And a much older problem, which is still completely fully solved, is the question of the wind stress and how the wind blows on the ocean and how rough the ocean is for the wind. This stress is usually supported by these very short waves, and so if you don't know well the directional distribution, you won't know very well the stress for the atmosphere. So how the ocean blows on the wind blows on the ocean is very important for that. And at some point, we've worked a lot using spectra for quantifying the energy at different scales. And as you start to look at smaller and smaller scales, so that's a very extreme case. Actually, I took this picture when going to the WISE meeting in 2001 in Canada. So this is very shallow water. And what you see here is what's called Wilton ripples. These are these very short waves, capillary waves that are generated on the crest of longer gravity waves. And you can see that they are not everywhere. Their position, so the position of the short waves is attached to the long waves because it is a curvature of the long wave which is going to generate this train of short waves. So it may look like a small things, which is funny to look at, it's beautiful, but actually it's important for some application, could be for Earth interaction. One thing I'm sure it's important for, and one thing I'm working on, and that's the reason I'm stopping here on my way to Vienna, is we're starting to build new satellites to be able to measure currents at small and smaller scales using Doppler radars. And the backscatter, how the radar waves is reflected by the ocean surface, depends on these small things. And the motion, the velocities is a function of where the short waves ride on top of the long waves. So this is a broad introduction of why people care about waves. I would think that, you know, for a lot of us, it's just beautiful, and so we want to understand and see what's happening. These are examples of polarimetric measurements. I've been showing this plot for, I don't know, 6-7 years. We collected that data 10 years ago. I haven't done nothing about it scientifically, and so it's starting to work with this kind of polarimetric data. What you're seeing here is a slope field in the x direction. As the waves breaking, and so this is a small scale, but you can see a lot of details in that picture of how the different waves are organized around the larger waves. And so you're probably all familiar with this image from Hokusai showing the great waves. It is beautiful, but it also has very interesting features. You can see the blue ribs inside of the breaking waves. But one thing I like to show to my students is all the short waves riding on top of the big waves, just to point to the fact that we don't only have the dominant scale of the waves, but we also have all these small scale structures. And recently I was preparing some slides for the student that came this week in class, and I found this beautiful picture taken in Southern Ocean. So from a distance, I don't know if you can see very well, but you have these large waves of probably around 10-meter wave height probably around 400-meter wavelengths, 500-meter wavelengths. That's 4 or 5 football fields. So these are very, very long. And on top of them, you can maybe see the structure of shorter waves riding on top of them, which are wavelengths of 2-3 meters. And for scale, this bird here has a wingspan of like 2 meters. But of course, it's hard to know where it is compared to, okay, so it's taken from a ship in the Southern Ocean, and very beautiful things to look at. Okay, now SWOT. So this is a project that has been keeping a lot of people busy for the last 20 years. I think it was proposed to ESA as an Earth explorer back in the 90s. It was called Water, I think, at that time. And the way it works with space agencies is a good ideas take a lot of time to come to fruition. The basic idea is that people were measuring the sea level to look at currents, to look at waves and other things with a system that only measuring straight down. And actually, SWOT has this old generation instrument, which is the Poseidon 3C, which is this antenna here, which is looking straight down. Maybe I should show it here. So here you have this antenna here at the bottom of the spacecraft. And it is, oops, let me put the pointer thing. So that thing is this good old altimeter like JSON and making measurement of sea level. So the dots here on this map of sea level would be the measurement for that. They're typically covering a swath of a couple kilometer wide. And you have these narrow strip, a pencil beam measurement of sea level along the track of the satellite. The main difference with SWOT, it also carries SAR interferometer. So there's 2 SAR antennas on the left and on the right. And so basically, these are radars that make images. And because we have 2 images at the same time, we can make some interferometry between the 2 radars. So each radar is measuring an amplitude and a phase image. And so you can look at each amplitude and phase, but also at the cross phase of the 2 radar and stuff like that. And from this geometry of the measurements, when you're looking at the phase difference of the radar echoes, the phase difference is actually giving you the surface elevation below the satellite across the swath. So this red-yellow map here is actually a map of the sea level across the Gulf Stream over something which is 120 kilometer wide. And so the satellite was launched in 2022. I was fortunate to be part of the science definition team starting in 2010, and now the science team. And so we're going forward with more data acquired. So we were really struggling to get the data and to see the stuff working because there was a bit of a problem on the satellite. One of the power amplifiers had got some issues, which was related to the, I didn't say it's a NASA and CNES collaboration, so the French Space Agency and the US Space Agency. And at the interface between people, there's always issues. And so the radar actually tripped off because it was detected some high voltage. And that was not, and the way it was planned between the instruments and the platform, which is French, and the American instrument, there was some miscommunication. And so for a couple of weeks, we had no data. They didn't know what happened. So they actually went to the spare. No, we're actually working with the spare, but probably the old one's still working. Anyway, things are working. It was launched in December. We started to get good data from March to July 2023. For 6 months, it was on this 1-day repeat cycle. So every day, it's coming the exact same data. So it's very nice to look at fast evolution of the ocean. And since the end of July 2023, it's been operating with a cycle that covers the entire globe with a repeat cycle every 21 days. So yeah, not the entire globe, but there's a few small diamonds at the equator that are missing, but small detail. And the name says surface water oceanography because it's doing both hydrology, so it's measuring the sea level, but also the land, water, so lakes and rivers elevation. And I will show you some of the first results from that mission that was just published last year and this year. It's also doing all sorts of other stuff like geology. So since I was stopping in Padova yesterday, and this is where Galileo was teaching, I should probably say something about the gravity field. So this paper published in Science earlier this year, showing the first maps of the anomalies of the gravity field. So what it's showing is the gradient, it's a horizontal gradient of the vertical component of the gravity field, okay? And the kind of details you can see here is in this region here. And so we have the big ocean ridges and all stuff. So what we see is actually from the sea level measurement, if you average the sea level in time, the main contribution of the sea level is a geoid, so the fact that the Earth is not uniform. And you get these variations that are of the order of 10 eodvos at the scale of 10 kilometers. So I didn't know what eodvos was. So these people that know gravimetry probably know that eodvos was a Hungarian scientist which looked at the gradients of the gravity field. And to give you a scale, so the gravity constant G, which is about 10 meters per second squared, if it varies over 10 kilometers, it would be 1 million eodvos. And so the signal here is less than 10. So we're measuring variation of the gravity field in 1 ppm, basically one part per million. And this is revealing abyssal hills, which nobody has seen before. So the details of the ocean floor, the maps, if you go on Google Maps and look at the background maps of the ocean, this is coming from Smith and Sandwell. So David Sandwell is now making this update on the map. So maybe next year, or I don't know when, Google Maps will have the updated maps with very detailed mapping of the ocean floor. So they're discovering sea mounts, they're discovering all sorts of structural geology of the ocean bottom. So this is the sea level average in time is giving you idea about the structure of the solid Earth. But the people that do ocean stuff, they want to look at things that are moving. So there's one of the recent paper looking at what SWOT can measure. So there's 2 examples. Maybe I'll start with the one on the right. So I'm sorry for the people in the back, it's a bit hard to see, but this is a piece in the Indian Ocean. So the colors here are showing the sea level anomaly between minus 40 centimeters and plus 40 centimeters. This is a SWOT pass. So you have 2 bands with high resolution data, which are reddish colors and these bands. And these arc-shaped bands and the stripes here are internal waves. So you can map internal waves, sea level anomalies, which are of the order of 10 centimeters at really high resolution, typically better than 5 kilometers, I would think. And then on top of that, if you actually look at the details, you can see swell, which are 500-meter wavelengths on top of these long internal waves. And then there's also the large-scale circulation. The bottom left picture is showing some plots of the South Africa. So you have these rings coming from the Agulhas current going into the southern Indian Ocean. And in this case, there is a small dot here with a sea level anomaly of maybe 20 centimeters. And this is a very intense, very small cyclone inside of this larger structure.
Excuse me, could you repeat? I didn't get what's the resolution of the SWOT on this level?
Okay, we don't know yet. So the data is given on a grid with a 250-meter resolution globally, okay? So this is way, 250 meter means that the Nyquist is 500 meters. So if you have wavelengths at 500 meters, this is like the limit you can resolve. But this is a global data. The actual raw data and the land data and some of the coastal areas is at something like 20-meter resolution, yes. So we started, okay, the problem with that, if you really want to look at the details at 20-meter resolutions, it's a SAR image with a phase and amplitude. And so people that have looked at SAR image with waves, they know that the wave motion will make some funny things in the SAR image. So we still are not clear about interpreting the spectra of the sea level in terms of wave spectra for short waves. But for the swell, I will show some of that. We know it works. But yeah, resolution globally is 250 meter. It comes back every 21 days at the exact same place. But the sub-cycle, so it will come with a slightly different geometry, typically every 10 days. So you can get a global coverage of the ocean every 10 days, a bit faster at high latitudes because of the polar orbit. One other example of applications, this is from a preprint you can find online. It's a paper submitted to JRL, looking at the impact of the currents on the waves and leveraging the fact that SWOT is measuring, so the backscatter, which is the strength of the echo, which is related to the wind speed. It's measuring the sea level elevation from which you can do geostrophy and estimate the currents. And actually, at every pixel of the SWOT image, you have an average phase related to the sea level, but the noise in the phase is related to the wave height. So you can actually make a map of the wave heights at high resolution. So right now, what is produced is maps of wave heights at 2 kilometer resolution. across this 120 bands. So there's a gap in the middle, okay, and we have the nadir altimeter in the middle. So we have these two bands of wave height, and you can start to see details which we knew from models that we expect. In the ocean, the currents are the main source of wave height variability at scales shorter than 200 kilometers. And we can see that here in the Gulf Stream, but you can see that also everywhere, even in the Mediterranean, you would see some really nice gradients with the currents. So it's something we just start to explore. The paper that explains the method for measuring wave heights was just published, I don't know, 2 months ago in IEEE remote sensing, and the actual algorithm has just been improved. So the latest version of the data, which is produced since 3 weeks ago, has been changed based on that new updated algorithm. So there will be some reprocessing of all the data in the coming months, but it's still very fresh, and every new release of the data has some new parameters and new things to look at. I will not discuss it here, but it will be presented next week in Vienna. There's also a direct measurement of the Doppler velocity from the surface. We hope to be able to get some full current measurement from that, from the velocity, a bit like a speed gun from the cops on the highway. But right now it's still in research mode, so we'll see what happens. Okay, and in the sea level, as you've seen, we can see a lot of details. And I started looking at this beautiful, well, to me it's beautiful, but maybe not to you, these kind of pictures of fingerprints of long waves. So this is, again, a piece of 40 by 40 kilometer in blue here. And this is coming from an area which is north of New Zealand. And this was taken, so June 11, 2023, and it was 5 days after a big storm south of Kerguelen Island. So this well actually went all around Australia and then started propagating into the Pacific. This particular picture has, okay, you can see the main orientation of the wave crest. This is oblique direction. So if you take a Fourier transform of this picture in C, you get this other picture, which is also called C because it was another figure, but anyway. And you can see the Fourier transform has a peak, and in yellow here, so it's symmetric, so you have two peaks in opposite directions. But we know from the data also has another information from the backsteppers. We actually look at the cross spectrum of this. We know the swell is actually coming from that direction, from the southwest, so it's consistent with the storm. And we have the wavelengths, we have the directions and all of that. But what was puzzling in this picture is a very small signal here, which if you haven't looked at it too much, doesn't look at the signal. If you actually look very carefully at the picture, you will see some vertical stripes. And if you follow the satellite, you will see the stripes turning around. And these small waves coming from the side are also swells scattered by an island 100 kilometers away. And these small swells have an amplitude of 3 centimeters, or crest to trough height, 3 centimeter wave height, with a wavelength of 1 kilometer. So this is about the detection level of SWOT is able to measure swell, which are 3 centimeter high at a 1 kilometer wavelength. So this is really something that I've never seen before. No other instrument can do that. Even buoys are not sensitive to this kind of measurements. So we actually have no way to validate this directly. Of course, we can do a lot of indirect things. So the data is consistent with other observation of swell when the amplitude is large enough, and for the small amplitudes, it's hard to tell. And so I'll now show you some details about one storm. And yes. Okay, so I have a movie. Let's see if that works. Movie doesn't want to work? Okay. That's okay. If people are interested, I have a bunch of YouTube movies of that. So it was following the satellite and showing the swell going from the storm in North Pacific to the south. And then I will discuss now about these storm properties. And so one of the questions was, okay, we're getting these very long waves, and how often are they important? How often are they happening? Should we care about 10 centimeter wave heights? For some applications, not, but other people, like seismologists, and I've been working with Piero Poli from University of Padova. Seismologists have known since the 1960s that there is a signal. So this kind of data here is measured from a seismic station in Africa, and it's showing the power of the ground motion as a function of frequency on vertical and time. And so here you have from May 5 to May 9. So we have 4 days of data here. This is from a paper by Ardhuin and Ardhuin about this kind of stuff. People that do waves, they know that this kind of signature is typical of swell arriving from a storm. Okay, so people have thought that well, this is clearly the swell creating some seismic noise, which are called microseism. But what was a bit puzzling is a horizontal band here, which has a constant, almost constant energy at a fixed frequency with a very narrow band, around 26 seconds. And this is recorded by all these stations all across the globe, and they all point to a source, which is in the Gulf of Guinea. So all these signals is coming from here. And so that's another paper, it's another story, but we actually found that the swell arriving there can explain that, and we actually were able to measure the swell from SWOT, and we have images of these very long waves with only 5 centimeter height at the same time as we have our signal, and when there's no waves, there's no signal. So that's proof that the waves are the source of that. The details of the mechanism of generation of this noise is a bit more complicated, but the main source initially is waves. Okay, so long waves happen on the ocean, and they are only generated in very large waves. So what do we know about these very large waves? And so people have been modeling ocean waves for marine safety for a long time. So Luigi here has been in this business for a very long time, since the at least the late 70s, early 80s. And so if you run a model and you can look at the wave heights and you can follow the maximum of the wave heights, what we did here. So this map here on the left is showing the tracks of the 100 top storms as a function of wave height for the last couple of years. So we start here in April 2023 until December of 24, and this is data for which we have SWOT coverage. The bottom plot is showing you the maximum wave height in the storm, so it goes from 10 meters to about 20, and you can see that there's a few storms actually going slightly above 20. And now we'll talk mostly about the storm Bolaven, which is an extratropical typhoon that transformed into an extratropical storm in October 23. And the other symbols, so the colors is a model, and the coloring corresponds to the time, and the maps is showing the same colors. We can actually, recognize different storms from the top. So the Bolaven storm was actually a maximum north of Hawaii, and then went to following the usual storm tracks from the west to the east. And on the bottom plots, the other symbols are the nearest satellite measurement of wave height. So that would be the red bullet. And you can see that in that case for Bolaven, the nearest altimeter measurement is only at 15 meters, whereas the model is giving us 20-some meters. So which is right? The problem is that satellite is never going right through the peak of the storm. It's always missing the storm. And so, okay, one of the questions is, can we trust the models? What Luigi has been saying a long time ago is that usually the models underestimate the peaks. So in this case, this is my own model run. I actually boosted the winds to make sure I was getting the peak almost right. And so when you actually compare the model at the place where the altimeter is maximum, there's almost no bias. The peaks are on average correct, but these are the peaks from the altimeters. These are not the real peak, because this is what happens. So that will be a map from the model at the peak of the storm. So the contour here is where we have wave heights larger than 18 meters. This contour actually was only started a few hours before, 10 hours before, and after 10 hours, it was gone. So the time when the waves get bigger than 18 meters is actually very short in time, like 1 day. And these are almost all the altimeter tracks we have in that area, and the different names of satellites, CFOSat, Sentinel-3B, Saral, Cryosat, Jason-3, and they all miss the peak because Sentinel-3B goes through the peak of the model storm, but it's coming there 5 hours early, so it's not at the same time. So it's very hard to say something from that, and there's a lot of uncertainty in what we can do, but okay. One thing we're sure we cannot miss is a swell coming from that storm, because when you imagine the very strong wind is like throwing a piece of rock in the pond, and then from that you get some waves. So even if you don't observe the rock falling into the water, you can observe the waves coming from that storm. And so what we do with SWOT, so the map on the right here is a maximum, the contours of the maximum wave height. If I only take waves longer than 21 seconds, which are really long waves, and I'm sure that SWOT can measure these. So 21 seconds would be a wavelength of about 700 meters. And for example, this is one SWOT track of Chile 7 days later, in red here. One piece of the track is this piece of ocean I was showing you at the very beginning, in which you see the crest of the swell and the Fourier transform in this plot on the left. And so then we analyze these images and extract this piece of the spectrum, which we know comes from the storm in the North Pacific 1 week earlier. Okay, so that's the procedure. We have all these kind of data, and we're going to look at the storm through the prism of this swell. Okay, so we do that at least for this track to begin with. So we have the mean wavelength as a function of distance, and the shape of that is a nice parabola. And the reason for that is very simple, is a dispersion relation of the waves. The phase speed is increasing linearly with the wave period, and so it goes quadratic with the wavelength. So the longer waves travel faster, and so when you make measurements away from the storm, you are measuring larger wavelengths on the top right here, larger wavelengths about 1 kilometer. And when you're measuring closer to the storm, these waves are slower, so they took the same time, but they arrived at a shorter distance. So only 12,000 kilometers, which is already pretty far away. So, this is where we are. The storm was, 12,000 kilometers away. So give you an idea. So this is something we know, no surprise. And then I was plotting the swell height, so the height of this swell as a function of the distance. And then I got this curve, which is interesting. It's very smooth, very repeatable. All the tracks, all the storms give the same shape. And that's something which puzzled me. And if you actually try to fit a function to this shape, you find that it's like the distance to the power minus 9. Okay, so why minus 9? Okay, so if you do a bit of theory and try to understand what's going on, the swell is coming from a storm, so you can try to think about what's happening in the storm. And so basically, each spectrum is like a puzzle, and we're trying to reassemble a picture of the storm from these different pieces of the puzzle and try to see what's happening in the storm. And it's what we have for this one storm. We have 109 tracks with swell on it, covering about 100 different spectra on both sides of the track of the satellite. So there's like 20,000 spectra, each covering 40 by 40 kilometers. So that's a huge area of ocean from which we have information. And all that area of the ocean is actually coming from this very small piece of ocean, 300 kilometers by 300 kilometers in the storm. So maybe there's some crazy stuff we could do, like backward propagating, inverse mirror crazy thing, but I'm going to do it a very simple way. Maybe there's better ways to do that. So what we're going to do is think about what's happening in the storm and what's happening with these waves. So we can assume that the wave periods longer than 18 seconds, which are observed by SWOT, are generated in a small area where the waves are strong enough and the winds are strong enough. And we're going to assume that they're all generated before October 17, or 17, sorry. So imagine at October 17 at midnight, we have a picture of the waves, which are 18 seconds, and this should be a small region of the ocean. So there's some theoretical work that tells us that the spectral density should be conserved along the propagation path. And then if you actually convert the spectral density and integrate it, you can actually look at the integrated energy. So that's a bit of mathematics here. So basically the observed energy is a sum of the spectral density integrated over frequency and directions. And at some point you're going to say that the spectral density is the same away from the storm and in the storm at different times. And so that can give us some idea that in the end, the observed energy should be a function of the spectrum in the storm, and then some other factors and stuff like that. So we have a relationship between the shape of the spectrum in the storm and the observed swell field properties. And if you do that, so first thing I did is, okay, well, typically people would assume that the shape of the wave spectrum, the energy as well as frequency, has this kind of John swap shape. It was coming from an experiment in the North Sea in the 1960s. And if you apply that and you try to look at what it should give at the swell height, you get this green curve. The waves very far away from the storm at large distances correspond to the very low frequencies. And if you try to fit the curve, and there's no way you can get the shape at the end to match the data. And this is basically because we have a lot of energy at low frequencies compared to what I think is happening. And so what I did then next is, okay, actually this part of the spectrum, we don't have much information about. Maybe it's wrong. And so if it is wrong, how should I correct it to fit the observation? And so if you actually have something which is steeper, like f to the power 17 on the forward phase of spectrum, then you get some nice fit to the observation. And okay, so why f17? Well, some people actually do look at wave-wave interaction. So the nonlinear evolution of the waves will transfer energy from short waves to long waves. So these are very academic simulations of what happens. You have some waves with no wind, with no braking, and you start with a red spectrum and you let it evolve. And because the waves are not linear, they will transfer energy from these short waves toward the longer waves as time goes by. So different curves are for different times. Right? So time equals 0, they put this funny shape of the spectrum, and after a few hours, I think the stuff is in hours, yes, they will evolve. That will evolve to a shape of the spectrum which is always the same and going slightly towards higher and lower and lower frequencies. But the shape of that spectrum in that region from 0.9 to 0.5 times the peak frequency is actually pretty close to f to the power 17. So that's one reason, maybe what I'm seeing, my assumption about the swell is not completely crazy. It's actually consistent with nonlinear wave interaction, which we know should be important for the wave evolution. Okay, and so one side effect of that is, okay, if we now accept that this is the shape of the spectrum and it gives us this shape of the swell field, well, the maximum of this curve here actually would correspond to the peak period in the storm. So we can now go and estimate the peak periods from all the storms using the swell data, and it was done by Tanya Posted, who's working with me on this project. And so now we have this bottom plot for all these storms we looked at in North Pacific. We have some values for the peak period, which, okay, how good is it? We're still trying to understand, but that is something that nobody has observed before, and so we're trying to make some sense with that. These storms I'm looking at, so Bolaven, the storm I was showing you before, is right here. So the peak here is about 19 seconds. And the cross here is a value I get from my model. And so in that case, it's not too far. The largest value we get is from Storm Eddy in December. It's about 20.1 seconds. Some of the storms are actually very different from the model. Well, 1.5 second difference. So is it real or not? What's happening in those cases? Maybe the model is wrong. So we need to investigate that, but we have some link between the peak periods and the, yes, and the rapid depth and storm. Okay. So one thing I'm working on now, still very much work in progress, is okay, we have these observations. Can we produce that with the models? And these are, for example, some example of the spectra in different versions of a wave model for the peak of the Bolaven storm. The main difference between the different symbols, so the red one is the red is typically the shape of the spectrum we get with a usual parameterization in wave models. For the four interactions is the discrete interaction approximation is coming from Hasselmann in 1985. But if you actually run the model with exactly nonlinear interactions, and you can do that now with the Gaussian quadrature method, which was developed by Lev Menov and implemented by Michel Benoit. You can actually run that, and you actually would get this very nice f to the power 17 forward phase. So in that case, you see the peak is not in the right place. The spectrum is much more pointy, peaky, and so this, okay, I'm making the claim that these models actually are better, but probably they need some tuning. And so this is, you have to start and undo the entire model. It's like you take off the engine and you have to rebuild everything again. And first thing I was playing at it, so. Yeah, I'm looking at the wave height as a function of latitude for one SWOT frac. So swell height in red on the left, and the blue is a model with this very better nonlinear calculations, and now the model is making these crazy big swings back and forth with the wave heights. And if you look at the periods, now you understand why, if you know how wave models work, the model is discretized in frequency. You have these steps because of this quantization frequency. This is because we have a very narrow spectrum, so we get what we call a Gaussian-Sprinkler effect, but in direction space. And yeah, you can rename that as a Gretz goes down the stairs effect. So we get this kind of shape like this dinosaur and some stairs, and right. And so the end story is okay. I'm trying to make it look like a Diplodocus, but I'm not there yet. The yellow curve is a bit better.
You have to activate on that.
No, no, in this case, no, because
And we'll finish here. So people are starting to chat and it's getting late. So basically, we're getting this new observation from SWOT showing the long waves as part of the sea level measurement. And there's also massive wave at the same time. So it's starting to show things we have never seen before. These very small amplitude swell with very large wavelengths. It seems that these are consistent with the idea that four-wave interactions are dominating the cascade of energy to long periods. And that's not completely consistent with the Jones-Swartz spectrum. So, you know, if you update the Jones-Swartz spectrum by changing the shape of the forward phase, you could actually have something consistent with observation. And yes, at some point the model will have to be updated. That's going to take a lot of work because if we take the engine apart, we have to build everything back up. And so you know, we can discuss that and other things. Thank you. So I don't know if there's any question.
Fabrice, can I make you a question? If you can then repeat the name of the book. So the shape of Jones-Swartz, how it happened that do you, from your understanding, was misunderstood?